So far, we have seen how to build a neural network that uses dense layers, or a DNN, to learn how to classify images, as well as the principles behind convolutions that will learn filters that can be matched to the features in images. Let's now take a look at enhancing our existing DNN to add convolutions to them and see the impact. To recap, here's our DNN code that we've been using to classify MNIST or fashion MNIST images. For this example, I'll use the fashion MNIST version, which is a little more sophisticated than handwriting digits, making it harder to get a higher level of accuracy. The model architecture is here, and it's a simple sequential which flattens the input and feeds it through dense layers. When we train a model with it, we'll be able to see the accuracy and validation accuracy reported back to us. And in this case, after 20 epochs, I get an accuracy of 89.53% and a validation accuracy of 86.77%. These results are good, but we might be able to improve on them using convolutions. Let's take a look. Here's a complete code of an updated neural architecture to use convolutional neural networks instead of a straight up DNN. First, we can see that our input layer, we will use an input shape, but it's a little different. It's now 28 by 28 by 1 instead of just 28 by 28. This is because the convolutional layer expects the image dimensions to be fully defined. So a color image will have 3 channels. So it'll be something by 3. And a monochrome image will have 1 channel. So it's specified here. Our image is 28 by 28, 1 channel. So 28 by 28 by 1. Our output layer will be 10 neurons as before, as we have 10 classes. We also have a flatten before we get into the DNN. This will occur after the filters have done their job. The filters will act on the image as we saw previously. So they'll still be rectangular, and once they've given updated pixel values, then we can flatten before we get into the DNN, and the network will behave as before. So let's now look at how to define the convolutional neural network. First, we'll specify the convolutional layers using conv2D. It's 2D because images have a width and a height, and we'll pass filters across them to change the image to extract features. Remember, the filter values will be learned over time. The pooling that we described previously is implemented by specifying max pooling as a filter. There are different types of pools, such as max, min, and average. For this, we'll be using max pooling, where we will take the largest value from the pool. Looking at the convolutional layers, we can explore the parameters. First is this number, which is the first parameter of the convolution layer. And this is the number of filters to apply to the images at this layer. So we have 64 filters that will be applied to the image at this layer. Remember that the filter values are randomly initialized and will be learned over time. The 3 by 3 here indicates the size of the filter. Recall that when we were talking about filters, we had defined a 3 by 3 filter that multiplied across the current pixel and each of its neighbors. This can be a different value. For example, 5 by 5 to look at neighboring pixels up to 2 pixels away and so on. And it's similar for pools, where the size of the pool is specified as a parameter, which in this case is a 2 by 2 pool. So we'll be picking 1 pixel out of 4. If we want different size pools, we can define them here. Remember that by pooling, we are reducing the size of our image, helping us to emphasize and summarize the features that we have extracted. Okay, now you've seen how to update your code to allow for convolutions. And you saw how you can improve the accuracy of a fashion MNIST classifier using them. Now you can try a collab where you'll see them for yourself.